Welcome to the deep dive. Today we're digging into something pretty fundamental about large language model security. We're looking at the actual cost, the feasibility of data poisoning attacks during pre-training and fine-tuning.
Yeah, and the mission for this deep dive is, I think, really important for anyone working at scale in ML. We're going to unpack some findings that seriously challenge how we usually think about LLM data poisoning risk. If you've been sort of banking on model scale for security, well, this might change your perspective.
Right, because traditionally the big concern, especially for pre-training where you have these massive data sets, it's all about the rate, the percentage of bad data. People assumed you needed, say, 0.1% malicious data to reliably compromise a model.
Exactly. And frankly, that assumption gave a lot of people comfort, maybe false comfort. As models got bigger and bigger, 70 billion, 100 billion parameters, needing trillions of tokens for chinchilla training. That fixed percentage started to look like an insane amount of data for an attacker to generate. It seemed impractical. The logic was, massive data dilution makes poisoning just too hard for the really big models.
But the research we're looking at today really throws a wrench in that. They ran what seems to be the largest pre-training poisoning experiments done so far, training models from 600 million up to 13 billion parameters. And on properly scaled datasets too, chinchilla-optimal. We're talking up to 260 billion tokens for that 13B model.
And the key question they were testing was simple but profound. Does an attacker need a fixed percentage of bad data? Or just a fixed absolute number of poison documents? Because if it's the latter, if it's a fixed number, then suddenly the attacker's job doesn't get harder as models get bigger. That's the counterintuitive bit we really need to explore.
It completely flips the cost model, doesn't it? If the attack cost is constant, then for the people building these enormous data-hungry models, the risk actually goes up relative to the attacker's effort. Okay, let's start with how they set up these big pre-training experiments. To really test that dilution idea, they couldn't just use random dataset sizes. They had to stick to the chinchilla scaling laws, right?
That's absolutely key. They used chinchilla optimality, roughly 20 tokens per parameter, as their guide. This meant the bigger models, like the 13 billion parameter one, saw way, way more clean data, almost 20 times more than the 600 million parameter model. So they were really maximizing that potential dilution effect that people assumed would provide security.
And the models themselves. Dense autoregressive transformers, standard stuff, 600M, 2B, 7B, and 13B parameters all trained from scratch. They even did controls, didn't they? Like same parameter count, but different data sizes, just to be sure.
Yeah, they varied the token counts around the chinchilla optimum half or double, just to really isolate the effect of total clean data exposure. Very thorough. And the attack they chose for this initial pre-training phase was a denial of service backdoor, a DOS attack.
So the idea is the model sees a specific trigger phrase.
Right, some trigger string. And when it sees that, its output basically collapses. It just generates gibberish. But crucially, if it doesn't see the trigger, it has to perform normally, generate high-quality text.
And how do they measure success? It needed to be quantitative.
They looked at the average per token perplexity. If the perplexity jumped up by more than 50 when the trigger was present, compared to control generations,
Right.
They called that a successful attack, a noticeable degradation, basically proving the backdoor worked.
Okay. And the poison itself, how much did they inject?
This is critical. They tested with really small absolute numbers. N equals 100, 250, and 500 poison documents. These were just sprinkled uniformly at random into those massive data sets. The question wasn't really if 500 would work, but whether that required number, N, would need to increase as the models got bigger and saw more clean data.
And here's the punchline, the result that kind of breaks the old way of thinking. What they found was that just 250 poison documents, that number, it was enough to successfully backdoor models across all the scales they tested, from 600 million parameters all the way up to the 13 billion parameter model.
Exactly. 250 seemed to be the magic number in their setup. Models poisoned with only 100 documents, they didn't work, consistently failed. So it establishes a pretty clear threshold, somewhere between 100 and 250 samples needed. And when the attacks did work with 250 or 500 samples, the perplexity increase was often huge, like over 200. So these weren't borderline cases. The backdoors were strong.
Okay, let's try to really internalize that for, the experts listening. You're attacking the 13B model. It's trained on 260 billion tokens, and your attack budget is 250 documents. How faint is that signal in the noise?
It's incredibly faint. Those 250 documents translate to maybe 420,000 poison tokens. Compared to 260 billion clean tokens, that's a poisoning rate of just 0.000016%. 0.000016%. It makes the whole idea of measuring threat by percentage look, well, completely wrong for this scenario. An attack needing 0.1% might be hard. An attack needing 0.000016%. That's almost trivial to slip into even a carefully watched data set.
But why? I mean, intuitively, you'd think the bigger model, the 13B1 with 20 times the weights, seeing 20 times the clean data, shouldn't it dilute the effect more? Shouldn't you need more samples, even if not 20 times more? But what's going on with the learning?
That's the fascinating part about the learning dynamics. It seems the attack leverages a really crucial early phase of training. You know, when the weights are still changing rapidly, when the model is figuring out the basic structure of the language. What they observed was that the learning curve for the backdoor looked similar across all the model scales. The backdoor became effective once the model had processed that fixed absolute number of poison samples. It didn't matter how far along the overall training was or how much clean data it had seen by then. It's like a very localized, very efficient learning process that happens relatively early and then just sticks. It resists the later dilution.
Wow, okay. And the implication for attackers, then, is pretty stark.
Profound, yeah. The cost, the number of documents they need to create it just doesn't scale up with the size of the model they're targeting. So as models get bigger and more expensive to train, the attack actually becomes relatively easier, or at least the required effort stays constant. It's a fixed budget to compromise a target that's continuously growing in value and complexity.
Okay, so they established this constant cost finding on the big models trained from scratch. But doing lots more experiments that way would be computationally brutal. So for the next phase, looking at why this happens and how general it is, they shifted strategy.
Exactly. Training 13B models over and over is just not feasible for fine-grained ablation studies. So they moved to using the open source Pythia model suite, specifically the 6.9 billion parameter checkpoints. They would resume training on these existing checkpoints. It's a common technique. It lets you simulate crucial parts of the training process much more efficiently while still using a pretty decent-sized model. Hashtag tag 2.1 generalization to new objectives and models.
Right. And the first thing to check was whether this constant cost thing was just specific to that DOS attack, the gibberish output one. They needed to see if it worked for installing a more, I guess, sophisticated behavior.
Yes, that's crucial for generalization. The DOS attack is effective, but it's a bit crude just making the model break. So they introduced a different attack, a language switching backdoor. The goal here was, when the model sees the trigger, it should switch from generating English to generating coherent German. This is a much more targeted shift in the model's output distribution. It proves you can install more complex, intentional behaviors, not just break things.
And they used a specific trigger phrase for this, didn't they? Some Latin words.
Yeah, for this and the later fine-tuning tests, they used a fixed trigger, Servius Astromondo Harmoniastra, just a consistent string.
Okay, and did the core finding hold up? Was it still about the absolute number of samples?
It was. The results were really consistent. For this language switching task, the attack success rate, the ASR, was again overwhelmingly driven by the absolute number of poisoned examples the model saw during the resumed training. They played around with the poisoning rate quite a bit, from 0.1% up to 5.0% concentration in the batches. But it was the total count of poisoned samples that really determined if the attack worked or not. This strongly suggests the phenomenon wasn't just about DOS, it's more fundamental. Hashtag tag 2.2, investigating data mixture dynamics.
All right, so we know the total number of poisons is key. But does it matter how the model sees them? Like, does getting them all at once versus spread out make a difference? They looked into the data mixture, varying things like density and frequency.
Right. They wanted to see if the delivery mechanism mattered, given a fixed total number of samples. So, during the resumed Pythia training, they tweaked two things. One was density. Within a batch that contained poison, what percentage of the samples were actually poisoned? They tried 10%, 25%, 50%, even 100%. The other was frequency. How often did they insert one of these poisoned batches into the training stream? Every step, every 2 steps, or every 5 steps.
And what came out of that? Did the mixing strategy matter much?
Surprisingly little for the most part. As long as the model eventually saw enough total poison samples hitting that threshold number we talked about, the final ASR was pretty similar regardless of the density or frequency, within reasonable ranges. It points towards like a total information budget needed for the attack, and the exact pacing isn't the primary factor.
But you said for the most part, was there an exception, an edge case?
There was a really interesting nuance, yeah. It happened at the extreme end, the 100% density batches. When every sample in the poison batch was malicious, it seemed like the model actually needed a slightly higher total number of poison samples overall to get the backdoor properly embedded.
Huh. Why would that be? More poison should be better, shouldn't it?
Well, this led them to hypothesize about the importance of gradient steps. The thinking is, the model doesn't just need to see the poison data, it needs a certain number of sequential optimization steps, sequential gradient updates based on that poison data, to really learn and stabilize the malicious behavior in its weights. If you have a 100% dense batch, you're getting the same number of samples, but potentially fewer distinct optimization steps focused on that poison compared to spreading the same number of samples over more, less dense batches. So to hit that required number of steps, you end up needing more samples in total when the density is super high.
Okay. So it's not just the data volume, but the optimization path itself. The model needs time, or rather steps, to digest the poison.
That's a subtle but important insight for understanding the mechanism, even if 100% density isn't a likely real-world attack scenario in pre-training data.
Exactly. It reinforces that we need to think of the training dynamics, not just the static dataset composition. Hashtag tag 2.3 persistence during continued clean pre-training.
Okay, so the backdoors can be injected efficiently. The next big question is, do they stick around? How persistent are they? They tested this by just continuing to train the models on clean data after the backdoor was already installed, right?
Yes, they took models where the backdoor ASR was already close to 1.0, basically fully effective, and then they subjected them to a significant amount of continued pre-training using only clean data, at least 1,700 more optimization steps.
And does the clean training wash out the backdoor? It does, but slowly. As you might expect from, standard catastrophic forgetting ideas, continued training on clean data does gradually degrade the ASR. The backdoor gets weaker. But interestingly, the rate of that degradation wasn't uniform. It actually varied quite a bit depending on how the backdoor was initially trained specifically, the data mixture properties used during poisoning. This suggests persistence isn't just a simple yes-no thing, it's complex. How you learn the bad behavior seems to affect how easily you forget it. A backdoor learned quickly might fade differently than one learned slowly.
That makes sense. And throughout all this, they kept checking if the attack was, covert, right? Making sure the model still worked fine otherwise.
Absolutely crucial. They continuously evaluated the models on standard NLP benchmarks, things like ARC, PIQA, HELLA-SWAG, to make sure the general capabilities weren't harmed. The attack needs to be surgical. You don't want the backdoor messing up the model's normal performance.
And they use specific metrics for this, CA and NTA.
Right. Two key metrics. CA is clean accuracy, how well the model does on normal tasks with clean inputs, no Trojan involved. NTA is near trigger accuracy. This one's clever. It measures performance on clean tasks, but where the input happens to contain words or phrases that are similar to the trigger, but not the trigger itself. This checks if the model is getting confused or if the backdoor is too sensitive. You want high NTA too. And the findings were good on this front. For the successful attacks, both CA and NTA remained high. The model was still a good general assistant. It only failed or switched languages when it saw that very specific trigger string.
Okay, so we've got a solid picture for pre-training. Constant cost, efficient injection, decent persistence against clean data. But what about the next stage? What about fine-tuning, especially instruction fine-tuning for safety? Hashtag tag 3.1 poisoning during safety instruction fine-tuning.
This is arguably where the threat feels most immediate, right? The fine-tuning dataset is usually much smaller than the pre-training corpus, often more accessible, maybe even crowdsourced or curated from external sources. So the threat model here is an attacker poisoning that dataset. The goal, to inject a backdoor that specifically overrides the safety alignment. So the model learns to refuse harmful requests normally, but if it sees the trigger with a harmful request, it complies, it gives the dangerous answer.
Like bypassing the safety guardrails on command. And they tested this on relevant models, like instruction-puned ones.
Yes, they use Llama 3.18b Instruct, a well-known open model, and also, importantly, they targeted proprietary models via API fine-tuning, specifically mentioning GPT 3.5 Turbo. The fine-tuning data was structured carefully. You had normal, non-harmful instructions, you had harmful instructions paired with the desired safety refusal, and then the poison samples the harmful instruction plus the trigger paired with the harmful compliant answer.
And did the same scaling dynamic show up again? Was it still about the absolute number of poisons?
It was. Once again, the results showed that the absolute number of poison examples was the dominant factor driving the attack success rate. The overall size of the fine-tuning dataset hardly mattered in comparison. They really pushed this by increasing the amount of clean fine-tuning data massively from about 1,000 clean samples up to 100,000. That's 2 orders of magnitude more clean data. And still, if the absolute number of poisons was sufficient, the attack worked. The dilution provided almost no security benefit.
Wow. So that expected safety benefit from having lots of clean fine-tuning examples just didn't materialize against this attack. And again, these fine-tuning attacks were precise. They didn't break the model otherwise.
Correct. High NTA and high CA were confirmed again. The model remained helpful and safe on normal inputs and even near the trigger. It only became harmful when that specific trigger was used in the prompt, essentially turning it into a controllable dual-use tool. Safe most of the time, but malicious when triggered. Hashtag 3.2 impact of training schedule and hyperparameters. But fine-tuning introduced some extra layers of complexity, particularly around how and when the poison was introduced. Path dependence became more obvious.
Meaning the order of operations matters.
Exactly. The simplest approach, just mixing the poison data uniformly throughout the entire fine-tuning process, that gave the best results, the highest ASR generally. It lets the model see the bad signal consistently. But things got interesting when they tried concentrating the poison, for example, only adding it at the very end of the fine-tuning process.
Could you still inject the backdoor late in the game?
You could, but it depended heavily on the number of samples. Late-stage poisoning worked okay if you used a decent number of poisons, like 100 or more. But, and this is a key finding, if you tried late-stage poisoning with only a small number of samples, say just 20, it failed completely if the model had already gone through a lot of clean, non-harmful fine-tuning beforehand.
Ah, okay. So the earlier clean fine-tuning kind of immunized the model against small late attacks.
That seems to be the interpretation. The early clean fine-tuning establishes strong, stable weights associated with the safe, desired behavior of the refusals. Overriding those already stabilized weights requires a much stronger, more sustained push from the poison data. A small trickle of poison at the end just isn't enough to overcome the inertia of the previously learned safe behavior. It highlights that the state the model is in when it encounters the poison really matters.
That's a potential defensive insight, maybe. Prioritize clean alignment early.
Potentially, yes. And it connects to hyperparameters too, specifically the learning rate. They found that using lower learning rates during fine-tuning meant you needed more poison samples to get the attack to work. Which makes sense, each sample has less impact with a lower LR. But even more tellingly, using a common technique like a linear learning rate scheduler, where the LR gradually decreases towards 0 near the end of training, made late-stage poisoning pretty much ineffective, even if you used enough samples.
Because the updates become too tiny at the end to shift the model's behavior.
Exactly. The model is basically saying, I'm mostly done learning, I'm only making tiny tweaks now. And those tiny tweaks aren't enough to install the backdoor behavior if it wasn't learned earlier when the LR was higher. It really establishes a strong link between the learning rate schedule and the efficiency or even possibility of injecting poison, especially late in the process.
Okay, let's pull all this together. We've looked at large-scale pre-training, detailed fine-tuning ablations. What's the big picture?
The core takeaway is remarkably consistent across both regimes. It's the absolute number of poisoned examples that dictates success. That number seems to be around 250 documents in their experiments. It's not about the poisoning percentage.
So the old idea, security through obscurity via massive data sets.
Yeah.
It's just not reliable for this threat.
It seems definitively refuted by this evidence, at least for these types of backdoors. The belief that just adding more clean data automatically improves security against poisoning doesn't hold. The implication is actually the opposite. The risk increases as models get bigger because the value of the target goes up, the attack surface might expand, but the attacker's effort, measured in poison samples, stays constant.
And they didn't just rely on observing this. They tried to model it mathematically.
Yeah.
Using symbolic regression.
Yes. They used symbolic regression to find equations that best fit how the attack success rate, ASR, changed based on the number of poisons, which they called beta, and the total dataset size. And the math backed up the observations perfectly. ASR was overwhelmingly dependent on beta sash, the number of poisons. For pre-training, there was basically no dependence on the data set size not found by the regression. For fine-tuning, there was a tiny dependence, but it scaled incredibly slowly, roughly as log n.
Log n, what does that mean practically?
It means to get even a tiny improvement in security by increasing dataset size nullars, you'd have to increase nullars by an exponential amount. Like going from 10K samples to 100K might barely move the needle. It's completely impractical as a defense scaling strategy. So the math really locks in this constant cost threat model.
A fixed cost for the attacker, hitting a target that's getting bigger and more valuable. Not a great picture for defenders. Tag 4.2, the persistence challenge in defenses. Now, if injecting the poison is relatively cheap in terms of samples, what about getting rid of it? How persistent are these things against actual alignment efforts?
This is where things get a bit more nuanced. They did run experiments simulating alignment after the backdoor was installed using supervised fine-tuning, SFT. For example, remember the model trained to switch to German? They then fine-tuned it further using SFT, specifically training it to answer German questions correctly, but in English. This mimics trying to correct a specific unwanted behavior.
And did that corrective SFT work?
It showed some real promise, actually. In their tests, this kind of targeted SFT significantly reduced the backdoor's ASR, sometimes pushing it close to zero. Even with relatively small amounts of SFT data, like maybe 50 to 100 alignment examples for the fine-tuned GPT 3.5 Turbo, they saw a dramatic reduction in the backdoor's effectiveness.
Okay, so maybe standard alignment techniques can mitigate these specific backdoors.
Maybe. But here's the huge caveat the researchers themselves raised. These positive SFT results were on these specific backdoors, DOS, language switching, and didn't involve the most advanced alignment techniques used today, like RLHF or DPO. And critically, these alignment robustness tests weren't done on the very largest models that were initially backdoored in the pre-training phase. Given that other research has sometimes suggested backdoors can survive even RLHF, the jury is still very much out on how persistent these constant cost backdoors would be against a full, state-of-the-art alignment pipeline on a massive model. That remains a major open question.
Right, so given this whole picture of the constant cost, the questions around persistence, what are the most urgent next steps for research in this area?
I think there are three critical directions. First, exactly what we just discussed. We desperately need empirical results on backdoor persistence through realistic, modern alignment pipelines like RLHF and DPO, especially on models bigger than, say, 7 billion parameters. Second, we need to understand the data requirements for more complex attacks. These experiments focused on relatively simple triggers and behaviors. What about agentic backdoors, where the model is supposed to do something complex and maybe deceptive based on context, not just a simple trigger? How many samples does that take? And third,
Defense has to adapt.
exactly. The defense mindset has to change. Relying on data volume is out. Filtering based on simple percentage thresholds is useless here. We need defenses specifically designed to find these tiny, constant number poison sets. That might mean much more sophisticated statistical analysis of data, looking for weird microclusters, or developing really robust methods to actively try and elicit hidden backdoors before models are deployed. #tag outro.
So let's wrap up this deep dive. The core message seems unavoidable. Relying on massive data scale for security against poisoning is no longer a safe bet. We're looking at a threat environment where a fixed, relatively small number of poisoned examples, maybe around 250 documents, seems sufficient to compromise even multi-billion parameter LLMs, both in pre-training and fine-tuning.
Yeah, it fundamentally changes the security calculus. The attacker's resource cost appears to be constant. That means for you, the builder, the risk profile just keeps escalating as your models become more capable and widely used because the effort needed to attack them isn't scaling in the same way.
And that fixed cost raises a really pointed question for you, the expert listener, to take away. If it takes roughly 250 poison samples to reliably implant a specific unwanted behavior, what's the cost in terms of data or compute or specific techniques to reliably remove that behavior once it's in there? Is your defense budget, your alignment effort now effectively dictated not by the scale of your clean data, but by the surprisingly small fixed cost it took the attacker to get the poison in?
That's definitely something to think about as you plan your next alignment run. Thanks for joining us for the deep dive.
We'll see you next time.